Hello, good evening everyone. I'm Vedant Vashisht and I'll be the moderator for this webinar. A quick brief about myself. I study business administration and a member of Code Arts at NCU. We at Code Arts believe in exploring and learning new things, bringing events for our peers to grow with us. For the same, Code Arts present this session in series of analysis and design of algorithm. So today, we'll focus on overview of dynamic programming and greedy techniques. Stuart Russell said, although greed is considered one of the seven deadly sins, well, it turns out that greedy algorithms often perform quite well. So we've got our special guest speaker, Mr. Vipul Srivastava. He is a software development engineer at Amazon. He have been doing Spot since 5 years, worked at SAP for 4 years after college, have been working at Amazon since almost a year, have reached among 25 top coders on Spot in the world and current second in India. So it's great to have you, sir. Seems I'm done here for now. We'll be taking questions in the later part of the webinar. So the stage is all yours, sir.
Thanks, Vedant. I'll be sharing my screen. I'll switch off my cam and we can move from there. Let me know when you guys can see. Are we good to go?
Yes, sir, your screen is visible.
Sure. So this is our agenda for today. I'll be taking everyone through the introduction of what is called a greedy technique or dynamic programming. I'll give some examples where greedy works. I'll give some examples where greedy fails and DP works. And then I'll just go through some techniques, some tips and tricks, and some things you should know to excel in these two topics. So let's start with what is a greedy technique. So basically, a greedy technique is where we just choose the most optimal choice we have at the present moment. Uh, like a very good example can be, let's say you are given an array of integers and let's say it has n elements and someone asks you to choose n by 2 elements or let's say 5 elements or x elements from the array given, and the condition is that the sum of all the elements which you have chosen should be the largest. So like, I think you get the idea. You can just sort the array and take the largest x elements or n by 2 elements as I have written here, if we are given that we have to choose n by 2 elements. So what we understand from here is like we are not concerned about the future choices and we are not concerned about our past choices. We are just being greedy and we are just thinking about like choosing what things can like give us an optimal solution at that present moment. As soon as we see the largest element, we pick it up. The second largest element, we pick it up, and we keep doing that till we have the number of elements we wanted, and we can take a sum and that will always be the largest. So that's what it's called, like local optimal choice, and we hope to reach the global optimal doing that. And the choice is already the most obvious one and the most beneficial one. So yeah, that's what greedy is in a nutshell. Whereas in DP, we check our subproblems. We are concerned about the past, what choices we have made, and we refer them to derive our future optimal solutions. And it is not necessary, as we'll see ahead in our examples, that the local choice is not the optimal one, and it doesn't guarantee us that we'll reach the most optimal solution at the end. And for those cases, dynamic programming comes into play. A simplest example, which we all are taught in school and in college, is a Fibonacci series. So Fibonacci series is basically Fibonacci series of n is equal to Fibonacci of n minus 1 plus n minus 2. And fib of 0 and 1 is just fib of 0 and 1 are both ones, always, that's fixed. And for every further choice, we see the previous elements we had and we make a sum of that and we keep populating that. So this is where the concept of looking at our subproblems comes in. We are we are referring the things we have already derived in the past, and we are using that to derive our future values. So this is basically what is dynamic programming. We use already found solution of subproblems to reach the bigger solution, and not necessarily the local optimum will reach the global optimum. We'll see the examples ahead. So here's our first example for the greedy technique. So this is a simple example, which I'm sure you'll all be taught, or you all must have already been taught. So this is basically the activity scheduling algorithm. The problem goes like this. You are given an activities. We have 6 here in our example. We have a start time and an end time for all those activities. And the aim is to take part in as many activities as possible, and the condition is like you can't work on multiple activities in parallel. Like at a certain given moment, you should be working only on one of these activities. You can't simultaneously work on more than one. So basically how we proceed here, like if you guys want, you can just think about it for a minute. The basic thing we do is we sort this whole activity array by n times. I'll show you in the next slide how we do that. And we'll always take the activity which is finishing at the least with the least time. Like, so if we sort it out, we'll get this. So here we had an activities, the activity with the lowest end time was A2. The next activity was A3. It was finishing at 4, and then one was finishing at 6. Then one was finishing at 7, and then 9. And A6 was also finishing at 9. So here we'll give priority to the start time. So when we sort, the A1 will come before A6. So the sorted list will look like this. A2 is the first. Then we have A3. Then we have A4. We have A5, A1, and A6. So if you look at this, this shows that we have sorted it based on the end times. Now the concept here goes like this. So choose the activity which is ending with the least time. So our first choice will be A2. Now we have to keep in mind that we can't work on more than one activity at one point. So when we go to the second activity in our sorted list, we have to check that this this activity A3 is not overlapping with the activity A2. So our condition is satisfied here. This has ended at 2 and this starts at 3. So the end time of the previous choice affects the choice of the next activity. So it doesn't basically affect it. You just have to decide if you are going to choose it or not. And there is a simple condition for that. They shouldn't overlap. So we can take A3. Then we move to A4. Now we check the condition again, and here it fails. So if you see, the end time is 6, but the start time is 0. So basically the start time is not greater than the end time of the previous activity. So we can't take this activity. So we'll have to skip that. Then we reach to A5. The last activity we took was A3. It was ending at 4, and this is actually starting at 5. So this is a safe choice to make. We'll take this choice. So the next activity in our final list will be A5. Then we move to A1. Now our condition fails. The A5 was finishing at 7 and A1 was starting at 5. We can't make this choice, so we'll have to skip A1. And we move to A6. Now the last activity we took was A5. The start time of A6 is 8, which is greater than the end time of A5. So we can make this choice. So like we saw here, we are not concerned about our future. We are not concerned about past. We are just concerned about one of our conditions. That is, the activity shouldn't overlap. And as soon as we encounter an activity which satisfies that condition, that it is not overlapping with the previous activities, we can make that choice, and it will give us an optimal solution at the end. So here the maximum possible number of activities we can take part is 4, and they are A2, A3, A5, and A6. Taking these activities won't violate our condition of overlapping the activities. So this is a good example of greedy approach. Another example is the partial knapsack problem. So the partial knapsack problem goes like this. You are given n objects. All the objects have a weight and all the objects have a value. You have a bag and there is a limit of how much weight you can carry in the bag. For our example, we have taken that as 7. So I can't put objects with total weight more than 7 in there. Now the partial knapsack has a condition that you can take that item fully, like you can take the whole item, or you can even break it into like partial items which will have less weight and less value, and you can take those as well. You can't take, like, if the item is there weight 1 and value 1, you can't take it multiple times, but you can break it. Like if you want just to take the half of this object, it will contribute 0.5 weight to your answer and 0.5 value to your answer. So what we do here is, for the greedy technique, we find the benefit per unit of weight, which is basically value upon weight. And I have put this column here, which I derived from as inputs. And the first item is 1 upon 1, so that is 1. For the next item, the value will be 5 upon 4, and that will be 1.2. For the third, 7 upon 5, and that is 1.4. And the last, 4 upon 3, and that is 1.33. Now we are being greedy here, so we'll take the item with the maximum ratio of value upon weight. And here it is the item 4 with weight 5 and value 7. So we take that, and we always have to consider that our total weight doesn't exceed 7. So when we take this item, it is the first item. So our total weight at this moment will be equal to 0 plus 5. 0 plus 5. And that is actually less than our total weight. So we are safe here. And our value at this point will be equal to 0 plus 7. And so we are safe in choosing this item. Now we see the next item which we can choose being greedy. So basically the next item which has the highest value upon weight ratio. So that will be our fourth item, which has weight 3 and value 4, and the ratio is 1.33. Now if we add this to our total weight, it becomes 8. And that is violating our condition of the total weight being less than or equal to 7. So here we can't take this whole item, but we are free here to like break it into smaller parts. So we can take 2/3 of this item. If we take 2/3 of this item, it will contribute to a weight of 2, and it will be equal to 7. And we can take the 2/3 of the fourth item, and the value which it will give us will be 1.33 into 2, because 1.33 was for 1 unit of weight considering this item, and we are taking 2 units of that item. So this is basically like 2 units of that one weight, one ratio. So that will be 2 into 1.33. And this will give us an answer of around 9.66. And this is the most optimal thing we can do here if we are allowed to like select the items partially. So this will give us an answer of 9.66, which can be the maximum weight, which can be the maximum value we can put in our bag. So I hope this is also clear. Now I have an example for the DP on the same concept, which I'll show you. And there, if we go by the greedy approach, it will fail. So let's go to the next example. And basically, the dynamic programming is of multiple kinds. You have one-dimensional dynamic programming, which means that you can achieve your answer, you can achieve your solution using a one-dimensional array. There are two-dimensional dynamic programming algorithms, which will be the knapsack algorithm, which I'll show you. There are three-dimensional also, but the cases are very few. Mostly, you will be able to get to an answer with a 1D DP or a 2D DP. Now, just like we saw previously in our first greedy example, that we had an array and our aim was to choose the element such that the total sum becomes maximum. Now here also we have an array. We can choose as many elements as we want. There is one condition here. You can't choose consecutive elements. Like, for example, if you have chosen 5, you can't choose 10. If you have chosen 10, you can't choose 9 and 5. So basically, just the element on the immediate right and the immediate left of your choice, you can't choose that. Now let's see if we apply greedy here, what answer do we get? So for greedy, the basic thing which we can do is just pick the element with the highest value first. That will be 10. Now, since we have picked up 10, we can't pick 9 and we can't pick 5. Now the next greatest element we'll be left with will be 2. So we'll choose 2. Now, in the vicinity of 2, there is 9, which was already crossed out because we chose 10. So there is no problem. And the last element which we are left with is 1, which was not crossed out. And we choose that. And that gives us a value of 1. And the total value we'll get will be 13. So this is the answer we are getting from the greedy approach. Now let's see if we can do something better here. So what we can do is basically let's forget about the whole array, and for a moment let's assume that we were given only one element here. So the array only had one. Now let's say this is our final array. So we were given only the choice of one element. So the maximum we could have done is 1. So at our 0th element, we'll have 1. We are assuming that we had only one element in our input array. Now let's put 5 in our input array. Now we go to the second index of our solution array. Now what you can do here. So basically you can't use the previous element because if you are choosing 5, you can't choose 1. So if we assume that we are going to choose 5 in our case, so the answer will be 5 because you can't choose 1 there. Now let's say you are given 10. Now what you can do here, so basically for every element, for this element whose value is 10, there are two choices. You can either take it or you can leave it. Now, if let's say that you decide to leave it, if you decide to leave it, the value here will be the maximum value which we got up to the previous element, because at this element the value we had, even if it was coming out because we had selected 5, it's fine because we have already assumed that we are not going to select 10. So in that case our value will be 5. And now let's say that we are assuming that we are going to actually take 10. Now, if we are assuming that we are taking 10, we can't refer this value because this has a possibility that the previous element was included when we found the answer to this subproblem. So we can't refer this, so we actually have to refer this. So this is 1. So we can actually add the solution of this subproblem where we had only one element to the subproblem where we are now having total 3 elements. So what answer we'll get there? The third element 10 plus the answer which we had got here, and that was 1. So this will be 5 comma 10 plus 1, and we'll take the maximum of this. So the maximum of this will be 11. So we'll have the answer as 11. So here we kind of get an idea what kind of recurrence we are getting. So if we call this answer array the sum array, so the sum of I is equal to maximum of sum of I minus 1. This is the situation. We have assumed that we are not going to take the ith element of our input array. So that's where the 5 came from. And then we are taking, sorry, this is wrongly typed. So we are taking the sum of I minus 2 plus A of I. So this is the situation where we are assuming that we are actually going to take the ith element. So we are actually going to pick the 10th element, the element with the value 10, I'm sorry, the third element, and the value is 10. And we are going to add the value which we got at I minus 2, which was 1. And we are going to take the maximum of it. And that's where we got 11 in our answer, and we put 11 here. Now let's move to the next element. Now we add 9 to our input array. Now we have 9. Now let's see the recurrence, what happens. So if we assume that we are not going to take 9, we'll get 11 here, because that was the solution of our sub problem, which was just at one index before the index we are currently on. And now let's see, like, if we decide to take actually the value 9, then what can we get? So if we take the value 9, we'll take 9 plus the solution which we had 2 indexes back, which was 5, corresponds to our recurrence here. So 9 plus 5, which will give us 14. And out of 11 and 14, 14 being the highest, we'll choose 14. Now the last element. So the last element, let's say we are not going to pick that. The answer will be, if we are not going to pick that, we'll have 14 there. If we decide to pick that up, we'll have 2 plus the solution which we had here, that is 11. Now out of 14 and 2 plus 11, which is 13, 14 is the highest. So basically the optimal choice here is that we don't take the last element in our answer, and we actually just copy this value here as well, and that will be 14. And the last index of our solution array will give us the final answer. So the maximum you can get out of this array, if you have given the condition that you are not able to take the consecutive elements, will be 14. And that is coming from 10. Yeah, so this is our final array. But here we took the first element, here we took the second element, here we took the first element and the third element, that was 11. When we came here, we took 9, and this 9 plus 5 was 14, and here it was 14. So basically the answer which we are getting is from 9 plus 5, dp 9 plus 5, which is equal to 14. Now you see here, greedy was not giving us the optimal choice and DP gave us the optimal choice. The obvious difference you can see here is actually DP had lesser number of elements which we had selected from our input array, but still it gave us a bigger value there. So this is the difference between DP. We move step by step. We make the optimal choice considering what we have chosen in the past. And the method we saw here, taking the input array and storing answers at every step, this method is generally known as memoization. So memoization is nothing but recording the answer to our previous subproblems. And with memoization, we can always refer to the solution from our previous subproblems, and we can make an optimal solution at that particular point of time. I believe this shows the difference between greedy and DP, and why greedy is not always effective in giving us the most optimal choice. This was an example of 1D DP. Now let's move ahead and go to the knapsack problem. Now this is the standard knapsack problem. The difference here from the partial knapsack problem is this is 0-1 knapsack problem. Now 0-1 knapsack problem has a condition that you can't take no partial picking of objects is allowed. Either you can choose to ignore a particular object fully, or you can take that object fully. Again, the constraint is there that the total weight should not exceed the weight allowed for us, which was 7 here. Now what happens, like, let's say if we do the greedy approach, let's sort it by value and weight. I have sorted it on the next slide. This is the sorted list. Value 1, value 4, value 5, and value 7. Now let's see if what we can achieve if we use the greedy approach here. If we use the greedy approach, first of all, we'll take 7. Our total weight will come out to be 5. We can't take this object because if we add 4 to 5, it will be 9, violates our condition. We can't take this object. We add 3 to 5, the weight becomes 8, violates our condition. We can only choose this object next with the value 1, and the greedy solution will give us a value of 8. So greedy gives us a value of 8. Now I'll show you how we can understand this using dynamic programming. So what I have done here is I have created a 2D array. This is an example of 2D DP. Now my weights are on the columns. So this is 0, 1, 2, 3, 4, 5, 6, 7. So basically the sub problems are the most optimal solution when the total allowed weight was 0. Then the optimal solution when it was 1, 2, 3, 4. And we have to go till 7 because our maximum limit was 7 as given by our input constraints. And we have 4 items. So we'll have 4 rows here, 1, 2, 3, 4. What these signify is like when we'll be populating this, but we'll populate row by row here. And when we are populating this particular row, we are assuming that we were only given one object, just like we did in this array. We moved ahead with this, assuming on the first index, we had only one element in the array. Then we had 2, then we had 3, then we had 4, and at last we had 5. That is the whole concept here. So when we are populating this row, we'll assume that we were only given this object, this weight. And sorting by weight is very important here. That is the first thing which I did. I sorted this list by weights. So when we are given only one object with a value of 8 and we reach this particular cell, so the maximum weight allowed was 0. The number of objects which were allowed were 1, and that was the first object, and its weight was 1, which is greater than the 0. So here we can't choose that object because we can't exceed this value here. So our answer at this particular cell will be 0 because you basically can't choose, you have not chosen any objects till now. Now we move to this index with this cell, and you can see the allowed weight is 1 when we are here, and the allowed number of objects is 1, which is the first object. The weight is 1, and we were allowed actually to take objects whose total weight doesn't exceed 1. So we can choose this object and our value will be 1. Now we reach this cell, the maximum allowed weight was 2, but the maximum number of objects which we could look at was only the first object. So basically, while populating the first row, the only thing you have to check is the column you are at, its value is greater than the weight of the column, greater than or equal to the weight of the first object, weight of the first object. So we can populate 1, 1, 1 everywhere because 3 is greater than 1, the value is 1. 4 is greater than the weight 1, the value is 1. 5 is greater than weight 1, the value is 1. And that's how it goes till 7. Now we come to a point where we were actually allowed to look at the second object as well. The second object has a weight of 3 and a value of 4. Now this whole column can be assumed to be 0 because only 0 weights are allowed and no object has 0 weight, and it won't ever have, like we are actually like relating it to a real world that every object has some weight and has some value, positive integers. So let's go directly to this cell where the maximum allowed weight is 1 and the number of objects we have are 2 with weight 1 and 3. Now, it is simple here to see that we can't actually choose the second object because if we only choose the second object also, its weight will be 3. And here, the maximum allowed weight was 1. So what we can do here is we can look back. We can look that till the previous object, was there any value allowed which we were getting here? And yes, it was. There was 1. So we just populate 1 here. Going to this cell, the maximum allowed weight is 2. Again, we look at the previous row. The previous row means like we are pretty sure that we can't take this object. Like I said, because the weight of this only object is also exceeding 2. So we have assumed like we know that we can't take this object. We have to make the most of the previous objects which we had. So we can just copy the solution from the top. This will be 1. Now we reach a cell where the maximum allowed weight is 3. Now this object will come into play because now we are allowed to take this object. Now there are two options. Either we take this object or we ignore it. Let's see what happens if we ignore it. If we ignore it, the value will come from the top, because that's the best we could do when we didn't have this object in our picture at all. The best we could do when we didn't have the second object in our picture, and the best value we were getting there was 1. So that will come down as 1. Now let's look at a case where we are deciding that we are actually going to take this object. So if we were deciding to actually take this object, the value would be 4. And now how much weight do we have left? We have already taken an object with a weight of 3. The maximum allowed weight was 3. So basically we can take another object whose value was 0. It's simple, like 3 minus 3, we get 0. Now, how do we see that what is the most optimal solution with value 0? So basically this object is covered. You have to look into the previous row, like till the previous items, what was the maximum value you were getting, and the weight was 0. So basically I minus 1, and the column will be the total weight here, which is 3, minus the weight of this particular object, which was 3. So this is 0. The column comes out to be 0. So basically dp of I minus 1, the previous row, and the column will be the column we are at, that is j, minus the weight of this particular object, which is 3. 3 minus 3, 0. We can pick this value from here and we can add it here. And we are going to take the maximum of these two, which will come down to be 4. So now you might get some idea about the recurrence. The recurrence is this. dp of ij is equal to maximum of dp of I minus 1j, which means we have ignored the current object. At that particular weight, the maximum value we were getting by not considering the current object, we will use that, plus. Now this is the comma, the case where we are going to pick the current object. So that will give us the value of the current object, plus the value which we got with previous objects. We are not considering the current object in this term here. So dp of I minus 1, we are going to the previous row, and j minus weight of the current object, because our columns tell us about the weight. They signify the weight we are allowed to have minus the weight of this object. So that's how we got 4 here. Now let's see what happens here. The maximum allowed weight we have is 4. Now the first condition, we are not going to assume, we are not going to take this object. That will be 1. Then we assume that we are actually going to take this object. So that will give us a value of 4 plus. Now 4 minus the value of current object, 4 minus 3 will give us a column value of 1. Our row will be this one where we had only the first object, and our column will be the total allowed weight was 1 when we subtracted this weight from here. So what value we had there? It was 1. So 1 comma 4 plus 1. What is the maximum here? 4 plus 1. That gives us 5. This is easy to understand. Now, if you can, don't consider the code here, just use your common sense. You had a bag which could contain a total weight of 4, and you had only these two objects. What would have been the optimal solution? To take both the objects. And the value it would have given us, 4 plus 1, which will be 5. That's what we got here. We continue like this. Again, we are not going to take this object 1, comma, we are going to take this object, which is 4, plus the value 5 minus the weight of this object, which will give us 2. The value here was 1. It will give us 1. So the maximum value we'll have is 5. This is not going to change, at least for this particular row, because this all is 1. And this will be 5. This will be 5. Right. Now we get to the third one. Now we are considering that we have the third object as well available with us. Its weight is greater than the current column, the current maximum allowed weight. We have to refer the previous row and just copy it there. It will give us 1. Again, it will give us 1. Now the total allowed weight is 3. The weight of the current object is 4. Again, we can't take this object. Just copy the value from above. This will give us 4. Now we come here. the value. Now we can actually take this object because the weight of this object is equal to the maximum allowed weight we have currently, which is 4. So this will give us 5, comma, sorry. So first we assume that we are not going to take this object, copy the value from above, 5, comma, the value which we could get if we were actually taking this object. So the value of the object itself, which is 5 again, you can see here, and plus we refer the previous subproblem, 4 minus the weight of 4, which gives us 0. The in the previous row at the column index 0, the value which we had was 0. So 5 plus 0. So here both the values are same. Maximum we'll get is 5. We come here again. First, we are not going to take this object. Copy the value from above, 5, comma. We are going to take this object, 5 plus the value we had here. So 5 minus the weight of the current object. What will it give us? It will give us 1. We go to the previous row, we see what did we have when the weight was allowed, when the maximum weight allowed was 1, and we were not considering this object, the value was 1. So we put 1 here. What is the maximum we can get? 5 minus 5 comma 6. The maximum we have is 6. We'll get that answer here. So considering these objects, these 3 objects, and if the maximum allowed weight was 5, we would get 6 as a value. Simple to see here. 4. We are picking up this object and we are picking up the first object. Total value is 5. Total weight is 5. Total value is 6. We move ahead. We are not going to take this object 5, comma, we are going to take this object 5 plus 6 minus 4 is 2. Again, we had 1 there. 5 plus 1 is 6. So the total value 6. Now we get here. Now we are not going to take this object. So we get 5 just from the previous row, same column. And we are going to take this object. So the value is 5 plus 7 minus 4. Now 7 minus 4 gives us 3. So we have already taken an object which was contributing 4 weight. The only thing which we can do is maybe pick up items which were contributing a weight of 3, because 7 minus 4 is 3. We refer this subproblem which we have already solved. We get the index for the column as 7 minus the current weight, which is 4, current object weight 4, that is 3, the previous row. What did we have here? 4. The value was 4. 5 comma 5 plus 4, which will be 9, and obviously 9 is a greater value. So we have 9. Now at this position, again, you can verify this with common sense. Total allowed weight was 7. You can only pick up whole objects, or you can ignore that object. So basically here we are getting these 2 objects. We basically picked up these 2 objects. The weight was 7 and the total value was 9. Now we come to the last object. So basically now we have all the 4 objects available with us. The weight is 5. Just refer the previous value, 1. Again, 1, 1, 1. Now, when we have a limit of 5, that's where this object comes into play. Now let's assume we are not going to pick this object up, 6. Just the value from here, 6, comma. We are going to pick this object, 7 plus 5 minus the weight of the current object 5, which gives us 0. 7 plus 0. 7 plus 0 gives us 7. The maximum is 7. We'll put 7 here. Now the total allowed weight is 6. Let's assume we don't pick this object. Comes 6 from the top, and we pick this object. 7 plus 6 minus weight of current object is 5. You get the index as 1. Go to the previous row. Look at the column index 1. The value is 1. 7 plus 1, that's 8. The maximum here is 8, and we put it here. Now here, First, we are not going to pick this item 9, comma. We pick this item up. So we have a value of 7. What is the value of 7 minus 5? That's 2. We come here. Now here we see the value was 1 plus 1. Now this is the first time we have reached such an example where actually ignoring the current element was beneficial for us. If we only had 3 elements, if we only had 3 objects, we were already getting a value of 9. And when we had 4 objects and we are assuming that we are necessarily going to take the 4th object, the maximum value we are getting here is actually only 8. 7 plus 1, which is 8. So basically, it is more beneficial for us here to not choose this object. So the maximum value we can have is 9. This value is the solution of our overall problem. And the first difference you can make out here is when we were doing this by greedy, we were actually, without even thinking, picking this object because this was giving us the maximum value. And when we use DP, we actually didn't pick that object because that was bringing us down. We are doing better by neglecting that object, and we got a value of 9. What did we get when we were doing this by greedy? We were getting a value of 8. So these are the cases where DP is actually more beneficial when we have multiple choices to choose an object, to remove an object. And the main thing about DP and greedy is when you encounter a problem which has actually to be solved by DP, you can solve it by greedy. And the first solution which will strike your mind will be the greedy solution. But in those cases, you have to look there that whether it is going to give us an optimal solution every time. And that's where the algorithm design and analysis as a concept comes into play. You have to analyze the problem. You have to keep in mind various techniques which might be suitable for that problem. And then you have to prove that which technique will actually be the most beneficial for that particular problem. So this is DP. The maximum value you can get here is 9. And you are actually getting that by choosing the second object and the third object. The total weight, 7. The total value, 9. I hope that was clear. Now, there are some things which are generally said about DP and greedy. First is subproblems depend on recursive strategies. Yeah, that is totally true. In this recurrence, which I just put down here, we are always looking at the previous subproblems. So we are always referring the previous subproblems, and that is kind of recursive. We are considering the new item, and we are calling the solution of the previous subproblems again and again. We are going there, and this is what is called as recursion. Like you solve Fibonacci series. The recurrence which I showed here, you must have been taught to compute the Fibonacci series by recursion. This is the iterative thing which I put it down, but this is basically a recursive technique, and every recursive algorithm can be transported to an iterative algorithm. Requires understanding but can be easily achieved with memoization. That's what memoization does for us. We always keep storing our previous results. We keep going back and referring them, and we just keep deriving the solution to our latest subproblem which we have at hand. So you need to understand what is recursion, what is going back and looking at the previous subproblems. As per my personal experience, doing a problem with recursion, writing a code which depends on recursion, which involves calling a function again and again, I find it complicated. There is another downside to that. Apart from being difficult to understand, a recursive solution is not very optimal when you talk about large problems or large softwares. We never put a recursive code to production level software. The simple thing there is, like, if you go deep into recursion uses the program stack. The program stack is not in our control. It is actually out of our control, and it can get overfilled and we can't monitor it. When it gets overfilled, our program will crash because every program has a limited amount of stack memory. So we always try to avoid writing a recursive solution. And that's where it is important we understand how actually recursion works. It works using a stack, and we can transport it to an iterative solution. Second point I put here is understanding of 1D and 2D arrays is must. That is simple. I think most of you must already be having that understanding. Sorting is must. Most of the cases will require sorting for greedy and DP both. Activity scheduling, we saw the first thing we did was sort the entire list based on the end times. Knapsack, we saw the first thing we did was sort the entire list based on weights or based on the ratio when we were seeing the partial knapsack. Now here one complexity comes when you are actually sorting this list by end time. When you swap two activities, you have to simultaneously swap their start time as well to keep the integrity of the problem. If you swap these two, like you put 2 here and you put 9 here, you have actually just changed the input of your problem. Basically, the start time corresponding this must be 5 and the start time corresponding this must be 1. So this can here you can achieve this using 2 arrays, and you can start sorting based on 1 array and keep swapping the corresponding elements in the second array as well. This is going to be quite inefficient, or you'll have to write a very big merge sort code which will be 150 lines in itself. This is where I would suggest you to get familiar with what are STLs, as I have written here. Above can easily be achieved by vector of pairs and using sort STL. So every modern programming language, Java, C++, they provide us with various complex containers. Vectors is one of them. It's just an array which we can modify to achieve certain things, and you can use pairs there. And we have multiple predefined functions, like there is a function for sort, there is a function for binary search. There are a lot of such functions when you start exploring the languages. And I would suggest understanding them, how to use them efficiently is quite important if you want to be an optimal programmer. And competitive programming is basically solving the problem in the least amount of time you can, writing the shortest code and minimizing the time complexity of the problem. So yes, these are all my advices. I hope you all understood it. And yes, now I'm ready to take any questions.
Okay, it was very interesting, sir. So let's see what questions we've got here. So the first one is from Yogesh Yadav. What are the disadvantages of greedy method over dynamic programming method?
So as per like disadvantages, there are no such disadvantages. The disadvantages are that you are not actually referring to the solutions which you already had. And the examples I showed you, they very clearly like show you that how important the previous subproblems are in achieving the new solution. And that's where greedy will always give you an answer, but it will not be the most optimal one. So basically, there are no advantages or disadvantages. It's just that it depends on the problem, that where the greedy method is the most efficient and where the dynamic programming method is the most efficient. So it all comes down to your analysis of the problem, and you have to, like, the best thing which I do is I take a pen and a paper, I write the problem there, and I derive the solution from greedy. From greedy algorithm, it's always very easy to use the greedy algorithm. And then I see, like, what if we can do anything better? And you can do that manually using a pen and a paper with an array of 5 elements. And if you see that you can actually do something better than what you got from the greedy technique, it's obvious that the greedy technique is going to fail there. So that's where you have to start thinking about some other methods. Dynamic programming will come to your rescue.
Okay.
I hope that clears it.
So Sahil Bhatia asked how dynamic programming is different from recursion and memoization.
Dynamic programming is just a term we use. So memoization and recursion are parts of it. Memoization and recursion is something which you use to achieve the dynamic programming technique. Dynamic, like let's say dynamic programming is the whole proper big concept. And the inbuilt parts of that are recursion and memoization. Like if you are doing a DFS or you are doing something, you are using a queue for achieving a BFS or a DFS algorithm in a graph. So the queue is just a thing which helps you, it's just a container which helps you perform BFS. So that's it. Dynamic programming is the whole concept, and recursion and memoization are techniques which help you to implement the dynamic programming technique.
Okay. So Vanshita Singh asked, Sir, if we are just starting with dynamic programming, can you suggest some resources?
Yes. So basically, I would always advise to use YouTube. There is a channel which I like a lot. I'll just put that in the chat. So a channel by Tushar Roy. Tushar Roy is a very experienced software developer. He has worked in Amazon for 4 or 5 years, and he's currently working in Apple. He has made a lot of videos on quantitative programming. He has made some videos on system design as well. And his videos are like, I find them the best. So I think that can be the go-to resource for learning competitive programming and dynamic programming as well. Dynamic programming, he has around more than 30 videos, and he has tried to cover almost all of the techniques we are using there.
Okay, sir. So Sunita Singh asked, what to do if we are not getting the logic for these questions in the beginning?
Yeah, it's very normal. And to be honest, dynamic programming is one of the most vast techniques we are using, because there is no problem. Like every problem is somewhat different. It doesn't have very conceptualized algorithms there. Like for greedy, we have some algorithms which are very standard, like the Dijkstra algorithm for graphs for finding the shortest path. But dynamic programming is somewhat very different from there. So you will certainly face difficulties. I myself face difficulties up to this point as well in doing dynamic programming. The best thing you can do there is go to the internet, find out resources, and try to relate the problem to some problem which you have seen. You won't be able to relate it 100%, but these are common techniques like the knapsack problem I showed you, making a 2D array, trying to relate the new problem to that, making a 1D array for like I showed you for the picking of elements problem, and try to relate the problem there. If you then also can't relate it, like if you are practicing on any standard platform, you will always find tutorials, you'll always find people who are trying to explain and solve your questions. You can go there, you can find a lot of people like me who are actively trying to help students learn competitive programming and be comfortable there. So you can reach out to all of us. And the best thing you can do is don't get demotivated and continue, and you will definitely improve with time.
Okay, sir. Once again, is dynamic programming important for interviews?
Yes, it is certainly important. It is actually one of the most, or you can actually say the most important topics for competitive programming, just because of its vast nature and the difficulty it offers. All the good companies will at least ask you one or two dynamic programming questions. Google, Amazon. I have appeared for these companies, and they focus a lot on dynamic programming. So yes, it is important. And the questions they will ask won't be a very high level dynamic programming solution where you'll end up scratching your head for an hour or two. It will be simple, but yes, it will be on dynamic programming.
Okay, sir. So Shipra Singh asks, can you suggest the basic topics that we should do before going to DP and greedy?
As I said, the basic algorithms you should be knowing before this are searching and sorting. You should be very much comfortable with arrays. You should be comfortable with STLs if you want to write a small enough code, a decent enough code, which can be explainable in a short amount of time. So yes, basically arrays, searching, sorting. Searching is basically a very simple, like searching is basically the most basic algorithm you should know before even starting coding. So yeah, arrays and sorting are the most important. Also focus on some standard template libraries and get yourself familiar with some advanced containers, like I told about vectors. And that's it. Like if you are happy with that, you can proceed to dynamic and 3D programming.
Where do we use a greedy algorithm and where dynamic programming?
Yeah, so like I said, there is no fixed concept behind that where you use a DP and a greedy, and that is where the challenge lies. That's why the both of these algorithms are confusing and challenging. And now this comes down to you, like based on the question, like I said, get a pen and a paper, get some examples, make some examples, write them down, solve the question with on pen and paper using the greedy approach, and just see like if was it possible to do something better with that small example. If yes, of course your greedy thing is wrong. If not, your greedy thing was right. The personal thing which I use is I don't try to prove my solution right. When I derive a solution on pen and paper or in my head, I never try to prove it right. I actually try to prove it wrong. I focus my energy on proving it wrong. And if after enough amount of effort I'm not able to prove it wrong, I go ahead and implement that. That
Okay,
also
sir.
doesn't guarantee you that if you haven't been able to prove it wrong, it is the correct solution. It might be that you are still messing up, but that is one thing which I follow and it kind of helps me.
Okay, sir. Sahil Bhati asked, what are pros and cons of memoization or top-down approach?
Pros and cons. So basically, top down and bottom up both use 2D DP. There can be some problems where the top down doesn't work as well as the bottom up. Like basically, it will work, but to visualize the solution, somewhere you will find it easier to proceed with the bottom up approach than the top down approach. Apart from that, the time complexity will be same for both. It will be a square of time. So for the knapsack, it was O of number of objects into the total weight allowed to us. And the cons of memoization, well, yes, memoization uses extra memory. If you do it by recursion, it won't use extra memory, but then actually it is using extra memory, your program memory, but you are not allocating memory apart from that in your program. Apart from that, I don't see any cons of memoization or top-down approach, and I think they should work in all the questions, and they are simply much easier than only implementing recursion for a certain problem.
Okay. So I, I guess that those were all the questions. So it was very informative, sir. It was really interesting to learn more. I really hope the audience enjoyed the webinar. Seems to be it's time that we wrap up the webinar, and we will be posting a feedback form, and then the people. Yes, sir. Okay, we've got one more question. Can we use geeks for greedy?
Yes, you can use Geeks for Geeks for Greedy, and like Geeks for Geeks and LeetCode. There are a lot of websites out there. The only difference between Geeks for Geeks and LeetCode, and these are not basically purely competitive programming websites. They focus more on interview questions, and the genuine problem which I have faced there is the variety of questions is very limited because they only have the questions which are asked in interviews, and that too in popular interviews. So I would always suggest, if you want to get proficient in competitive programming, pick a platform like Codeforces or Spotch. But yeah, Geeks for Geeks and LeetCode are good platforms, but they will limit you just for towards the interview preparation, and it's always better to use some more intense platform to learn competitive programming.
Okay, sir. I guess we'll wrap up our webinar over here. It was great to have you over here, and it was very informative. And as I was saying, there will be a feedback form, so you guys can fill it up, and then we'll see.
Thank
So
you.
I guess.
Thanks for inviting me.
Okay. Thank you so much, sir.
Bye.
Bye bye.